our study of circles, and we're going to add some more things in. So like I said, every day we're going to take what we've known and add more tools to our toolkit to talk about more parts of circles. But as a quick review, since we had class last week, then there was a STAR test, then there was a long weekend, I'm assuming we've forgotten a little bit. So let's review. Last class we learned about central angles. A central angle is an angle that if a circle contains an angle whose vertex is on the center, it's called a central angle. And that's kind of like a duh, central angle is in the center. Notice it actually has to be in the center. So in our little image here, angle 2 between A, O, and C is our central angle. It goes from the sides of the circle to the center of the circle. We learned a couple classes ago that the central angle is the same measurement as the arc. So if I were highlighting the arc here, the arc created by that central angle is this little piece between A and C, the pizza pie crust. So the measurement of that green central angle and the measurement of the pizza crust are the same number. If one of them is 55, the other one is 55. Last class, we also learned about what's called an inscribed angle. An inscribed angle contains a vertex that is on the circle. Let me go answer the phone. Okay, so let me say that sentence again now that the phone is done. An inscribed angle is an angle whose vertex is on the circle. So if we look at A to this point over here to C, that's angle 1. Angle 1 is called an inscribed angle. It like reaches across the entire pizza. You shouldn't cut a pizza this way, but you can. In this way, the relationship between this weirdly cut pizza slice and its arc is that the inscribed angle measurement is half of the arc measurement. Last class, when we dealt with this formula, we actually said 2 times the angle, and we're going to specifically call it the inscribed angle. 2 times the inscribed angle is equal to the arc. That's what we used last time. And what I did on these notes is I just moved the 2 to the other side by dividing. Dividing by 2 is like a half. So you can put the 2 on the side of the inscribed angle or a 1/2 on the side of the arc. Your reference sheet, the green piece of paper on your desk, is going to have the 1/2 version. The 1/2 version is what most textbooks and what the internet will mostly use. But you know that means you can just double the angle to equal the arc. That's what we did last class. But what we can do now is kind of extend that idea to cut out a middleman and say if an inscribed angle and a central angle intercept the same arc like they do in our picture here, they both have the same pizza crust, then the inscribed angle blue measures half of the measure of the central angle green, which leads us to the formula. The inscribed angle is equal to half, so this is the inscribed angle, is equal to half of the central angle. Or if we don't like using fractions, what we can do is I wrote this down wrong. That's so embarrassing. You need to change this word for me. This should be double the inscribed angle equal to the central angle. Wow, that's so embarrassing that I wrote that down wrong. So this should say inscribed, this should say central. Double the inscribed equal to the central the same way you double the inscribed equal to the arc. My bad on that one. I knew that looked weird. This is why you proofread things. So you double the inscribed angle to make it equal to the central. Or you take half of the central to make it equal to the inscribed. Sorry about that. Okay, so if we use this idea and practice just real quick, these are the kinds of questions we had last class. We're going to find the indicated measurement. The first one, 1A, says to find the measure of angle BOC. First of all, we need to figure out where that is in my image. If I find angle BOC, okay, I know that BOC, if I follow those letters, goes from B to the center O out to C. What kind of angle is that? Is it an inscribed or is it a central? Central. So we know that whatever BOC is, this arc BC is going to have the same measurement. Okay. The second part of this is going to ask you for BC. So those are the two things we're looking for. The only piece of information you're given in this image, the only number, is this inscribed angle BAC. So we have to think about the relationship between the inscribed angle and the central angle, or the inscribed angle and the arc. So my question for you, because it's right above this, the formula we're going to use, either the 1/2 version or the double version, and I know we like the double version better, so we'll stick with that for right now, even though you can use the 1/2 version. We are going to double the inscribed angle, which is angle BAC, and that is going to be equal to the central angle, angle BOC. We know the blue angle measurement is 55, so I can replace angle BAC with the number 55 degrees, and that means that all I have to do to find angle BOC is double the number 55. So I do 55 times 2, and I find out that angle BOC is 110 degrees. And voila, I have that first answer, that angle BOC is 110 degrees. Every time you find a value when you're dealing with a complicated image like this, it's really helpful to add that number into your image. So I'm going to add 110 degrees to my picture, because part 2 becomes really easy now that I see that. Part B, I guess, is asking you for the arc length of BC. Well, what's the degree of this arc if this central angle is 110? Remember, the central angle is exactly equal to the arc. So if that central angle is 110, what's the arc? 110. They're exactly equal to each other. The central angle and the arc have the same degree measurement. So if I find one of them, I immediately know the other. That's what we did last class. You guys did levels for this. I actually made you do 12 levels, whoa. But we did really well on that, and then we took a STAR test, and then we had a long weekend. So I get that it's a little fuzzy, but hopefully that's back in your brain, because we're going to add more tools to our toolkit. Our second theorem we're going to really discuss today, it's our first new one, is called the tangent and intersected chord theorem for an inscribed angle. It says if a tangent, so touching the circle once, and a chord, touching the circle twice, intersect at a point on the circle, then the measure of each angle is half the measure of its corresponding intercepted arc, which follows, because that's exactly what we did before. If we double the inscribed angle, it's going to be equal to the arc. That's the same formula, because you can switch that around like it's printed on your paper and say that the inscribed angle is half of the arc. The inscribed angle is half of the arc. No matter which way you go around that circle, the inscribed angle would be half of the arc, and the inscribed angle would be half of this major arc. So really, that's the same formula as before. We're just really talking about it in terms of a tangent and a chord. So if we look at practice problems 2, 3, and 4, they're going to use this same image over here. It says if CD is tangent to the circle, find the indicated measures. And the first thing we're going to find is arc length AB. So I think it'd be easy if we highlight the things we're looking for here. For this first one, we're looking for this arc length AB. The only number I was given in this problem is this 70 degrees right here. Is this 70 degrees somehow related to this arc AB? Well, doesn't this intercepted angle right here, ABD, basically surround that arc? This is technically the pizza crust for this weirdly cut pizza pie slice. Do you see that? Which means the intercepted angle is half of this arc. Or that if we double the intersected angle, so we're going to double that 70 degrees, that way it's equal to the arc. So what is 2 times 70 degrees? 140. So we know that this arc length right here is 140 degrees. Like I said, it's very easy every time you work with these kinds of problems to add your information to the image as you find it. Again, This is a tangent and this is a chord, which makes an intercepted angle. Double the angle equal the arc, or half the arc equal to the angle. The next question here asks me to find AEB. Ooh, interesting. If I'm finding AEB and I follow from A to E to B, that's like the rest of the circle, yeah? All the way around a circle is how many degrees? 360. And if I want everything around the circle except for this red part, what do I do to find this purple arc AEB? I'm going to do 360 degrees minus that arc I've already found to be equal to my arc that I'm looking for, AEB. So what is 360 minus 140?
220.
220. So I know that this arc is 220 degrees. Because the whole thing has to be 360. If part of it is already 140, you just take that part away and you have what's missing. Now the last part here asks you to find the measure of angle ABC. So if I was finding ABC, I'm going from A to B out to C. I'm looking for this intercepted angle, the angle between a chord and a tangent line. What's the relationship between the pizza pie crust and the slice of pizza that touches the circle? Say again? Tangency, yeah, B is your point of tangency. But what is the relationship between this angle created at B and this arc length that we just found in purple? Let me go back a second. If we were looking at this side of the little circle, how did we get 140 again? We doubled the 70 because this side of the angle that I've done in highlighter blue is, if we double it, we get the arc. So if we have the arc, what could we do to find the angle instead of doubling it? Divide by 2. The opposite of doubling is taking a half. So if I know this arc length is 220, what can I do to find the angle that would go right here? 220 divided by 2. What is that? What is 220 divided by 2? 110. So I know that ABC is 110. If I was showing my work on this, I would say that if we doubled angle ABC, it would be equal to the 220 degrees. So I would just take a half of each of those to find angle ABC. Divide by 2, divide by 2. We'd get that angle ABC is 110 degrees. You can do a lot of this math in your head, but if you're showing me your work, which you should, this is the sort of work you're showing. 100%. So Joseph just noticed that this is a line, yeah? What do lines have to add up to be? All the angles that make a straight line. 180. What's 70 plus 110?
180.
This also makes sense. So if you just use the idea that these two angles are supplementary, you could again find 110 degrees. So all of the geometry rules are not gone. We're still using those line rules. We're just applying them to circles. Great notice. For the second practice problem that uses number 5 and number 6, we're going to use the image here. Now, it doesn't have any numbers in the image, but the numbers are here. It says, if the measure of arc ADB is 220, so this is where I recommend having a highlighter or some sort of marking with your pencil. We're going to go from A to D to B. So if I go from A to D to B, that means I'm going this way around the circle. It says that is 220 degrees. And the measure of angle ABD, so if I find that angle ABD, that measurement is 21 degrees. Oh, I didn't use a highlighter. Let me try again. ABD, and that's 21 degrees. It says to find the indicated measure. Okay, first things first, we are looking for the measurement of arc AB. arc AB, if I follow those letters, and AB means go from A to B as quick as possible, I'm going to go this way. We kind of already did this problem. All the way around the circle is how many degrees? 360. If this much is 220, how do I find the purple? I'm going to do 360 degrees. Ooh, I missed a 0. 360 degrees minus what I do know, which is 220 degrees. And I'll get the measurement of that arc that I care about. That's going to be arc AB. How long is arc AB? What is 360 minus 220? 140. Fabulous. So I'm going to add that to my picture. I like adding all of my numbers to my picture as I find them. Next question asks you to find the measurement of ACB. Here's where highlighting gets kind of weird. ACB, if we follow that one, is from A to C down to B. So I'm looking for this corner piece right here. Not the arc, but the angle in that like weird intersection point. So I personally think there's too much going on here right now for me to find this angle. And I forced you to do it along with me. Do you notice that I've redrawn this triangle ACB here on your paper? I think it's helpful if we take it out of the image just to look at it for a second. The things we know is that angle B is 21 degrees, and we're looking for angle C. We have to do some work to make this happen. Okay? The work that we need to do here is we need to decide what this angle A is so that we can find angle C. The reason I know we need to start with A is because A is on the circle. So if we notice this point of tangency is on the circle, what's the relationship between this red arc, the pizza pie crust, and the angle it creates? What's the relationship? You double the angle to equal the arc. Okay, so we know that we are going to double the angle A to equal to the arc, and that arc is 220 degrees. How do I find angle A? Divide by what? 2. So what is angle A? Which is 110. Okay, I know that this angle is 110. I know that that means my angle A is 110. Throw it back to triangles. What do all triangles add up to? Ooh, that's circles. Triangles. 180. Yeah, circles are 360, triangles are 180. Okay, so now that we know all triangles add up to 180, what we can do to find angle C is we can do 180 minus the 110 minus the 21 degrees, and that would be equal to angle C. So do that math for me real quick. What is 180 minus 110 minus 21? We should get 49 degrees. So we know that angle C, which is what we were looking for, ACB, is equal to 49 degrees. So this formula really is the same formula we used last class. Double the angle, equal the arc. It's just going to continue to add in with things as we learn more about circles and more about the parts of these circles and their angles. Going to the back, we're going to learn 2 new formulas because we have 2 new theorems. Do you notice something different about this, before I even get into it, about this circle compared to the circles we maybe used last class? Maybe something to do with like this center point right here. Say again? I can't hear you.
The lines are intersecting.
The lines are not on center. This is a different type of problem. Last class we had central angles because they literally went to the center of the circle, like the actual center, not just inside it, the actual center. But we also have theorems when angles are just inside the circle but not in the center. Look, it literally says it right here. So when angles are inside the circle but not in the center, we have a different formula. It says if an circle contains an angle whose vertex is inside the circle, then the measure of the angle is half the sum of the measures of the intercepted arcs. So this time, it's not double the angle equal the arc. In fact, it is double the inside angle. This is a different word. Double the inside angle equal to the sum of the arcs. So we have to add the arcs together. Sum of the angle equal to the arc. And let's color code this picture for us for a second. If we were finding, why are you doing this? If we were finding this circle right here for angle 1, this is the inside angle. Notice it is not in the center. To find that, we'd have to double that angle and set it equal to both arcs AB and DC. Do you see how those make like a bow tie across the circle? You use both the pizza crust on one side and the pizza crust on the other. You have to add them together. So you double the inside angle equal to the sum of the arcs. So if you look at an example here, number 7, I've already worked it for you. It said find the value of x. First of all, locate where x actually is, because it's not always in the same spot. Is x part of the angle or part of the arc? Arc. So we know we're going to make sure we put an x value on the arc side. The inside angle here, the one I have a number for, is 75. But then I also have the arc 58. So what I say is if I double that inside angle, which is my blue 75, it should be equal to both arcs DC and BE added together. So I take all the numbers from the image that I have and the variables and I put them together. The inside angle is 75. This arc is x. This arc is 58. At this point, once you double 75, I used inverse operations here, but this is a box method question. As long as you solve it for x appropriately, which I did by subtracting 58 from both sides, you get that x is equal to 92. I want to see on all of these problems today that you have written down the correct formula, because there are now going to be a bunch of formulas to choose from. So not only do we have double the inscribed angle equal to arc, we now have double the inside angle equal to arc plus arc. I need to see that written down so I know you're using the correct formula. Can we try one together? For number 8, we're still looking for x. It says find x. Where is x in this picture? Is it on an arc or on an angle? Angle. Okay, great. So if I highlight the way I've been highlighting, we have the angle x, which creates two arcs, arc AB and arc CD. My formula that I would set up is I would write down that if we double the inside angle, that word inside is not the same as inscribed, so I make sure to write inside angle, is going to be equal to the two arcs added together. So I'm going to say arc AB plus arc CD. Double the inside angle equal to the sum of the arcs. Okay, cool. So we fill stuff in where it belongs. What do I put inside these parentheses right here? What's my inside angle? X. Fabulous. What is the AB arc measurement? 92. What is the CD arc membership measurement? 50 degrees. At this point, you have set up the geometry part. It's just an algebra problem to solve. If I were solving this one, I would multiply 2 times x, that's 2x. And I would add 92 and 50 since they're both plane degrees. 92 plus 50 is 142. I don't need to subtract in this problem like I did in the one I did for you. What do you need to do here to solve for x? Divide by Very good. Okay, so we divide both sides by 2. We get that x is equal to 71 degrees. Fabulous. So it's really just a simple formula. Double the inside angle equal to the sum of the arcs. The problem with these kinds of problems is that you're going to have to choose the correct formula to use. It's not always going to like set them up easily like this. So if it's inside and not a central angle, you have to do double the angle, inside angle, equal to the sum of the arcs. Then we have one more theorem to learn today. And it's going to be pretty obvious what's different about these problems, but what's different about these circles? Where do those two lines meet? Way outside the circle. We have a different theorem, different formula, when the vertex of your angle is outside the circle. This is called the angles outside the circle theorem. Lovely name. It says if a circle contains an angle whose vertex is outside the circle, then the measure of the angle is half the difference, not sum, difference of the measures of the intercepted arcs. Or if we change that to where we're doubling something instead of taking the half, we would have double the outside angle. See how that word changed to say outside angle? Equal to the difference, which means I'm going to do the big arc minus the small arc. Not adding anymore, we're taking the difference, we're subtracting them. So if it's outside, you change your formulas. We double the outside angle to be equal to the big arc minus the small arc. Now it's pretty obvious what I mean by big arc and small arc, but just so you can, oh look, I wrote it on there, I forgot I did that. Do you see the difference in the big arc and the small arc? Same thing here, you have the big one and the small one, and then the big one and the small one. Yes? So we're always gonna do big minus small so we get a positive number. Okay, let's see how this works. I did number 10, so if we look at that one real fast, notice that in my problem here, I noticed I have a big arc, and I have a small arc, and then I have my inscribed angle that's on the outside. So I set up my correct formula that is double the outside equal to the big minus the small. And I really should have put the arc markings over here. So if you would add those for me, that would just be better. Big arc minus small arc. You could use letters if you wanted, but there's not enough points on the circle to name them. So I'm just going to call them big and small. I should see this written on your paper for each problem. I should see the formula you're using. That way I know you're using the correct one. But when I plug everything in, what is the measure of my outside angle? What's the number in that little crevice right there? 28. So the outside angle is 28 degrees. What is the measurement of the big arc? What does it say along the big arc? 4x plus 8. See how I put that right in the spot where big arc went? What does it say on the small arc? What's that measurement? 3x plus 2. Cool. We didn't have to worry about this when we're adding stuff, but when you're subtracting stuff, there's a distribution moment. This little minus sign needs to be distributed to everything inside that parentheses if there's more than one thing. So if you notice what I did is I took this and I said negative times 3x is negative 3x, and negative times positive 2 is negative 2. We distribute, yeah? I also doubled 28. 2 times 28 is 56. At this point, since it's a more complicated problem, I'm going to assume most of us would do the box method. So if you want to write down for yourself that this could be box method if you wanted. I just showed inverse operations because that's actually my preference. But what we do is we combine our like terms. 4x minus 3x is 1x. 8 and minus 2 is 6. Subtract the x to the other side, which is 56 minus 6. So we get that x is 50. This is probably more complicated or the most complicated kind of this problem that you could see. Most of them are going to be a lot easier and maybe less algebraic. In fact, the one we're about to do together is completely less algebraic. Can we do that one together? Let's go. Thank you, man. Let's go back to number 9. Okay, I notice immediately that my angle is outside of the circle. So my spidey senses are telling me, all right, you're probably going to use that outside the circle theorem where they're subtracting. I look on my reference sheet for the formula. Now your reference sheet has the 1/2 version, but you know you can just move that 2 to the other side. So I write down my formula, and I'm going to say if we double the outside angle, it should be equal to what? How do I finish this formula? Big arc minus small arc. Yeah. So I need to look at my image, and I need to find the measurement of the big arc. What is the measurement of the big arc? What's the measurement of the small arc? Fabulous. I know everything I need to plug those values in. This highlight didn't work. So here we go. What is the number for the outside angle? What is that measurement? 38. What's the measurement for the big angle? X. What's the measurement for the small angle? Okay, fabulous. Once I've plugged everything in, that's done with geometry. We just have to do algebra. We always check if we have to distribute since there's a minus sign. Do I actually need to distribute this negative sign over here? Is there more than one thing after the minus sign in parentheses? No, this is just a number, but it's always good to think that you could potentially have to distribute that negative to subtract both terms. But what I can do here is I can double 38. So we do 38 times 2, which would get us 76 degrees. And we know that 76 degrees is equal to x degrees minus 72 degrees. Using inverse operations instead of the box method, what do I do to solve for x? To get x all the way by itself. So x is already positive, right? Okay, so you're kind of trying to move the x to the other side? Can I make it easier? What if instead we move this guy to the other side? If I want to move this to the other side, just because x is fine being on the left side. I know it's, or the right side. I know it's weird. We normally have it on the left, but it's okay to leave it there. How do I get this to move? Plus 72. So I'm going to just do plus 72 on both sides. And since that's just a degree measure, I can add it with the other 76. And I would get 76 plus 72, which is 148, is equal to x by itself. And this is why I didn't want to move x. Isn't x already solved for x? It's by itself, right? We didn't even need to move it because it's plain and by itself. So voila, we know that x is equal to 148 degrees. But Jordan, the way you were wanting to solve it would work. It's just more work. So do it if that's what you see. I'm just trying to save us some time and work. If x is chilling by itself, just move all the constants away from it. It can solve it backwards, essentially, where it's on the right side. Okay, we're going to give GimKit another chance here to see if the server's fixed. We're going to just play a game, hopefully, that has these formulas. And it's going to probably just ask you over and over again, which formula should you use? So you would either say the arcs are equal to each other, inscribed is half the arc, inside is half the sum of the arcs, or outside is half the difference of the arcs. That's the sort of thing you're going to be picking over and over again. Yes? Yes. Let's see if GimKit came back alive. Oh, I left this on again. Man.